So we're continuing our discussion of modeling, and our first model up is an example of tank mixing. And the important part about this is really it's not so much about the tank, it's just other things can be modeled in exactly the same way. For example, we'll take a look at a money model that will be basically the same thing. Okay, so in our tank we have this 300 gallon capacity tank with 200 gallons of brine. So there's salt water in the tank. And so we're going to be modeling the amount of salt in the tank at time t. Okay, and so the incoming is 1 pound of salt per gallon, and it's coming in at a rate of 4 gallons per minute. I should have said initially we have a concentration of 1/4 pounds per gallon. We're going to assume that there's a little mixer here at the bottom. So this is a well mixed solution, and it's being poured out at a rate of 4 gallons per minute. Okay, so how should we start? Well, the first thing we want to do is label our notation. So let Q of t be the thing we're modeling, and that is the amount of salt. So Q of t is the salt in the tank at time t. And let's check our units. That is in pounds, and time is in minutes. Okay, and that's important because when we look at dq over dt, right, the units will be pounds per minute, and this is going to be how we model. We want to check to make sure that our units are right. Okay, so finally we want to model how the salt changes in the tank. So the way the salt changes is pretty common. The rate of change overall is going to be equal to the rate in minus the rate out. Okay, and again, that's going to be pounds. We need to make sure our units are matching up. Pounds per minute. Good. Okay, I'll kind of go back and forth there. So dq over dt is equal to, the rate in is 1 pound per gallon, but that's not the right units. I do see I have 4 gallons per minute, and now you might notice that the gallons cancel and we're left with the right units. Okay, so therefore the incoming is just going to be 4, and then we subtract the rate out, so that's 4 gallons per minute, and then that's going to be again pounds per gallon, and so we need to know how many pounds and how many gallons are in the tank at time t. So we know that it's actually Q of t is the pounds in the tank at time t, and how many gallons are in the tank at time t? 200 gallons. We know it's 200 because notice that the rate in, 4 gallons per minute, is equal to the rate out, and so the amount of water in the tank does not change, so that's going to stay 200. Oops, 200. Good. And then let's simplify our differential equation now. Q prime equals 4 minus 1 over 50 times Q. And do we know Q of 0? It's not 1/4, right? That's the concentration. We have to multiply 200 by 1/4, and so that would be 50. Good. So can we solve this real quick? Notice that is of the form y prime equals ay plus b. And so can you write down the solution from that? If you can, excellent, because it just makes things go faster. Remember this, so this is, maybe I should write this over here, c e to the at minus b over a, right? That's what you're looking at here. All right, and so simplifying that, we get 200. Okay, now we have our initial condition to put in. So if I put that in, I get that 50 is equal to CE to the 0 power plus 200. So C is equal to minus 150. And that gives me my final full equation. Q of t is equal to minus 150 e to the minus t over 50 plus 200. Okay, now it's always good to do a reality check here. Does this equation make sense? So what's in particular, what's happening as time goes to infinity? As time goes to infinity, this first term is going to go to 0. First term to 0, right? Which means that you're going to be left with 200. So therefore Q goes to 200. Now, is that what it should go to? Let's go back up here. If as time goes to infinity, you might think that the concentration of salt in the tank at time t should go to 1 pound per gallon, right? Because that's the only thing that's incoming. You're flushing everything else out over time. And so we will have 1 pound per gallon times 200 gallons, which will give us 200 pounds of salt. So this does make sense then, and this is our good solution. Good job. Okay, now I'm going to do something a little tricky, and I'm going to come up here and I'm going to say, okay, this all worked very well as long as this 4 is equal to this 4. Suppose I were to come in here and I were to change this to a 5. How does that now change the problem? Well, for one thing, you'll notice that if it's going out at 5 and coming in at 4, we're losing 1 gallon per minute, right? So how many gallons are in the tank at time t? Let's make a note over here. So the incoming is at 4 gallons per minute. Outgoing is 5 gallons per minute. So we lose 1 gallon per minute. Okay, so what's the equation for that? So the amount of water, or brine I should say, in the tank at time t will be 200 minus t now. Good. So in fact the rest of the differential equation looks almost identical. Q prime is equal to 4 stays the same because we didn't change the incoming, but the outgoing now is going to be 5 gallons per minute, and now we're multiplying that times pounds per gallon, and now if we have Q here, we have 200 minus T here, right? And by the way, we might notice that T is only going to be able to run from 0 to 200, right? Q of 0 is still 50. Good, because what happens at time 200? You don't have any salt anymore. The tank is dry. Good. So can we solve this differential equation? What does this differential equation look like? This is going to be, I'll go ahead and rewrite it. Do you recognize this form? That is a linear differential equation, so we have to have a what is that called? An integrating factor. So our integrating factor is going to be e to the integral 5 over 200 minus t dt. So what do we get from that? That's e to the minus 5 natural log 200 minus t. I like to use absolute values there until I'm sure that everything's good. Simplifying that, I get 1 over 200 minus t to the 5th power. Good. So now I can write my differential equation as q over 200 minus t to the 5th power prime is equal to, now I multiply the right hand side by that as well, so I'm going to have 4 over 200 minus t to the 5th power Ah. So when I integrate, that's going to be minus 4 power, and so the 4's are already there. So I'm going to have Q over 200 minus T to the 5th power is equal to 200 minus T to the minus 4 power plus C. Good. And so let's go ahead and wrap this up. Q of T is now, multiply both sides by 200 minus T to the 5th. 200 minus T plus C times 200 minus T to the 5th. Good. And leave your answer in that form. Now we could solve for C, right? Let's go ahead and do it. We can do it quick as a bunny here. Q of 0 is 50, so 50 is equal to 200 plus C times 200 to the 5th. Now I'm not going to multiply that out. Leave that as 200 to the 5th. Oops. And so C is going to be minus 150 divided by 200 to the 5th. Okay, and so you would just plug that in here, and that would give us our solution. Very good. I've run over time. That is the solution to the tank mixing problem in two themes, or two variations. One variation is input equals output. The second is where they are not. Okay, so I'm going to come back and take a look at another model, interest rate model, and maybe a parachute.